So basically, in Android, everything you see on the screen, every little button, every text, they're all layers and layers and layers of buffers. And all of these buffers need to be kind of combined together into what you see on the screen, and that is called compositing. Normally, we think of this as being done by the GPU. And so you have all of these different buffers, and then the GPU kind of squishes them all into one frame, and then sends it out to the display. But really, on mobile devices as well as even desktop hardware now, there's a display controller that sits in front of that that can do some fairly simple graphic operations, and that includes doing things like compositing. And this is really nice because for a limited set of buffers, we're able to push these out and have the display do the compositing. And that basically allows the GPU to either be left off to save power, or we could let it be busy filling buffers with things to draw. Now, usually we have more than that small set of buffers that the display controller can show. So we still need to have the GPU compositing some and then kind of pushing the results of that to the display as well. And so really this deciding which layers are going to go to which planes in the display and which are going to be squished down by the GPU, this is the job of the hardware composer. So now I'm going to try to cover a bit of history and background. Originally in Android, we had the frame buffer device T. This was part of kind of the Gralloc code. It was just a simple way to access the frame buffer device. It provided just a simple post hook in order to push that frame buffer to the display. Then, with Ice Cream Sandwich, a number of different vendors had done their own things in the intervening years to accelerate things. And so the Android developers needed a HAL to kind of abstract away those differences. And so basically, they created the HardwareComposer 1 HAL that basically allowed them to kind of abstract overlays and 2D blitters. It was pretty simple. Had 3 interfaces just to prepare, which basically allowed you to configure things. Set would do the draw, and then vsync, basically a callback when the draw was done. With Jellybean, they introduced the Android sync framework. This is a little more complicated. Basically allows kind of a way of kind of tracking the ownership of various buffers as they move through the graphics stack. Basically allows you to enable some amount of parallelization as having multiple devices work on the same buffers. And to me, it's kind of conceptually similar to condition variables, but they're able to be nested somewhat. So trying to kind of go over kind of why this is needed. The original just single buffering kind of a simple case where people would draw into a buffer and then display that buffer, ideally on the vsync, but quite often you'd end up the case without any control that the GPU is drawing into the buffer at the same time that it's being displayed. And this creates kind of tearing, which I'm sure everyone's seen, is some point where you have basically 2 frames that are being displayed at the same time on the screen. The canonical solution to this is to use double buffering. Basically, you just have 2 buffers, and you have the GPU right into one buffer, and the other buffer being displayed, and then on the vsync, you just switch the pointers, and you can go on like that without any tearing. But again, when we're talking about having those layers and layers of buffers, it's actually more complicated. We're dealing with buffer sets. And so the GPU is going to be writing into a set of buffers, and then we have a set of buffers that we need to display. And so really there's another step in this where we have to kind of set up how those buffers are going to be composited in the display controller. And so now we basically have 3 stages that we have to deal with, and we want to be able to keep all of these busy. So kind of the simple next step there would be to add triple buffering. And so this keeps every stage in the pipeline busy, but it has the downside that we are basically increasing the amount of latency that you have on things like touch events by 60 milliseconds. And so that could be a big negative for interactivity. So, oh yes, a little dance there. Ideally, what we want to be able to do is have the GPU being able to draw into the buffers at the same time that we're setting up how those buffers are going to be composited in the display controller. And that way we can basically still only have 2 buffers and minimal latency, but keep everything busy. And in order to do this, we need to have some way of knowing when both the GPU and the display setup are finished with their work. And this is what the Android sync kind of provides. These timelines, these sync timelines, are basically per device. So the top one might be something for the GPU. The bottom one, let's say, is for the display controller. And you're basically able to just kind of mark points in time when certain work would be done. And so, for example, you could set a sync point that's on 2, which might be when the GPU is done drawing into a set of buffers. And then on the display controller at time 8, it's going to be finished with its configuring the buffers and ready to display. And at that point, the nice thing with these sync points is that they can be wrapped up in a sync fence. And once all of the sync points inside of that fence have fired, that sync fence will fire, and we know that we can push it out to display. So the next step in sort of the Android graphics history was the atomic display framework that showed up with Lollipop. This is really nice because it allowed kind of a way of providing sort of all or nothing configuration changes to the display controller. It avoids tearing and glitches, but kind of more importantly also avoids getting into bad hardware states, because sometimes you can lock up hardware if you set up the wrong things. Often when you have a number of these planes that you're going through configuring, if you get through all down to the last one and then you find some error that the controller can't actually display that, backing all of that state out is really complicated. And so this basically provided infrastructure for that kind of management of that state changes. The other cool part with this is that it was tied to the sync points, so they could basically pass in a sync fence with the display settings. And then once that fence had fired, they had known that everything was done on those buffers and they could be displayed. So to kind of go through an illustration of how this might be useful, here's kind of a standard Android home screen. And we've got 4 simple layers: a status bar, launcher UI, navigation bar, and a background layer. All of these are 32-bit alpha blend buffers. The only one that's maybe interested is the background layer, which might be a fairly large buffer that we're doing a viewport crop on. And we have some friend that calls in on some sort of secure video chat tool, and we've got basically 2 more layers we have to deal with. We've got some alpha blended UI that we need to kind of put on top. And then we also have the picture-in-picture video, which might be a secure buffer in a different format. And so now we have more layers than we can really display at one time in the display controller. And so we want to find some way to solve this. And so we need to kind of squish the bottom set of layers down in the GPU, and then we can push this out to the display. Now when we look at what actually changed there, we went from the status bar, launcher, navigation bar, and background layer to the picture-in-picture UI, the picture-in-picture, the status bar, and the GPU squish scene. And ignoring, because obviously the X and Ys of each of these buffers and the sizes are going to be slightly different, so that's kind of a change that would be constant across these. But if you look at kind of just the formats that we're dealing with and the other display properties that would have to be changed, you've got, for the status bar to the picture-in-picture UI, it's mostly the same, so just the X's and Y's are going to change. The launcher UI, we went from basically a 32-bit RGBA buffer to a secure buffer, so we now have to switch in secure mode. We also have to set it to YUV mode, because it's in a different format. The navigation bar and the status bar are basically the same, just X's and Y's change. And then on the last one, we went from basically a viewport cropped to a GPU squish scene. And so we need to change that buffer crop. And so you can imagine that if we're trying to make this transition between frames, we need to make everything happen all at once or something odd could happen. So if we got through basically everything except for the last thing, you might run into kind of a glitch for a frame where that crop property was still on the screen, and so it would kind of scale or probably redraw in a different way. So that's not what we want, and that's really kind of what the ADF provided. With Nougat, basically the HardwareComposer 2 HAL was introduced. This basically shows just kind of how complex the HardwareComposer had gotten over the time. So it's now 43 methods rather than 3. So it's gotten to be kind of a lot of complicated code. The other change here that was notable was that it moved to non-speculative fencing. This is pretty subtle, but basically instead of the fences signaling that the content's no longer needed, it was signaling that the content had been displayed. And then there's additional support for multiple displays in the HardwareComposer 2. So outside of the Android world, stuff was also changing in the kernel community. So in 4.6, DRM Fences landed. In a lot of ways, this is sort of just bizarro Android sync. The concepts are very similar, but the names are different, and they're just close enough to be really confusing. So instead of sync points, we have fences. Instead of sync fences, we have sync files. And then instead of timelines, we have contexts. But conceptually, it's basically very similar. And then in 4.10, the atomic KMS and DRM code landed, thanks to Robert Clark and lots of others. And at a high level, this is very similar to Android's ADF, but it's actually properly upstream, which is really nice. It allows for that all or nothing setting of display settings and signals with DRM fences instead of Android sync points. And this landed in 4.10, but Marissa Wall backported it to Android 4.9, so it's usable for devices using 4.9. And that gets us to the DRM Hardware Composer. Alrighty, so the DRM Hardware Composer was a project that was done by the Chrome OS team. It was implemented for the Pixel C device, and it uses the DRM and KMS interfaces. It was a Hardware 1 Composer implementation. They did prototype a Hardware Composer 2 implementation that did utilize the Atomic KMS interfaces, but that wasn't anything that actually shipped on a device. My understanding, after kind of a little bit of idle time, Robert Foss and Rob Herring in the community kind of picked this up and started working on it to get it to work on various dev boards. And so they've managed to get it working on QEMU with Virgil, the DB410, the DB820. It's been gotten to work on the Raspberry Pi 3. And we've also got it working on HiKey and HiKey 960. Actually, as of last week, the DRM Hardware Composer is the default for kernels 4.14 and above. And if you want to find out more, you can go check out the GitLab project there and see we've got kind of a small group of folks who are working on it. So as far as the goals for the DRM Hardware Composer, to some extent, just to validate the Atomic DRMKMS is functionally equivalent to ADF for Android uses is part of the goal there. Another nice thing is that with these dev boards, we don't have huge teams kind of behind us to develop, to get things all working. And so quite often the easiest solution with graphics is you enable the frame buffer device and let Surface Mailer just kind of handle it. But that really is pretty passé in the upstream community. They really want folks to be using the DRM KMS interfaces. And so this basically provides a working hardware composer that uses DRM and KMS that's kind of mostly works by default. There's a minimal amount of system-specific code that you might need to write. This is an importer for buffer importers, and then the planner that helps make sure that it can display things for, or it can order the layers on your DRM driver. And then basically it allows the systems to share kind of the rest of this kind of very complicated logic. And then another goal here is also to help motivate vendors to start moving to DRM and KMS display solutions. As far as the current limitations, so obviously it requires 4.10 or newer, or in Android you can use Android 4.9. There's some of the code that had been done for the Pixel C. There's kind of a fancy pre-compositor work. It was fairly NVIDIA specific, and it was really only for the Pixel C. And since that's no longer an active device, that had been since dropped. We also have the case where a lot of the devices that we have got it up and running on are fairly rudimentary, I guess, compared to devices that ship. The HiKey devices, for example, only really support a single plane, so there's not really much device compositing being done. And another issue kind of is that the importer and the planner code are actually tightly tied to the Gralloc implementation. So this makes it a little fragile in some cases because changes that happen to this external project can break or the DRM hardware composer. So we have to kind of keep things tightly aligned with those external Gralloc implementations. And overall, the code probably needs a fair amount of cleanup and generalization as well. As far as the to-do, probably, I think there's kind of some major cleanup is needed in the validate and plan logic. I've taken a couple swings at this, but not successfully yet. But hope to keep on working on that. It would be really nice. There was a lot of cool optimizations that were done for the Pixel C device. I'm not sure if they actually shipped or they were just at the prototyping stage. But they were able to do optimizations around squishing layers that weren't changing to try to further do power savings to avoid waking up the GPU. We also need write-back support. Some of the folks at ARM have actually submitted code to do this. I'm not sure if it's actually been enabled on real hardware or just in emulation, but it's something that definitely want to see validated on other hardware and generalized. And then just kind of in general, we need wider support for more advanced hardware. While I'm talking about the DRM Hardware Composer, I also wanted to mention the libDRM and Mesa 3D projects. These are all freedesktop.org projects. If you wanted to have an open graphics stack, these are the ones that you would probably need. They've all been recently updated in the AOSP tree to be closer to the upstream branches. And we've been doing a fair amount of work trying to upstream any AOSP changes in order to keep AOSP as closely aligned with upstream as possible. I think this is really important because I really want to be able to regularly test the upstream branches in Android. This is sort of similar to the work that we do with the upstream kernel community, where we really want to be able to test the upstream kernel to catch issues, and that helps create confidence when we move to newer kernels. And the reason why this is important is in the past these projects had been used on other shipping devices, but once a device ships, Google developers tend to get fairly conservative about changes, and so we don't want to, we don't want to end up having to lock down those projects on an older version because the potential risk in moving forward might break devices in the field. And so I want to make sure that we're able to kind of stay current and stay on top of the tip of those master branches upstream so that we can do a lot of testing and make it so that we are confident that we can move forward without breaking devices. So this is where we get into the hand-wavy possible futures space. So Google has deprecated ADF. From an upstream perspective, atomic KMS and DRM is really the only way to go. Unfortunately, many vendors still utilize their own legacy fbdev devices or drivers, and this is a little bit of a pain. Now, the vendors who are doing that, they may have good reason. It may be that the atomic KMS and DRM interfaces have some functional limit that folks aren't aware of. But we need to basically find those and address those, and in order for that to happen, we need vendors to start getting involved. One of the cool things that happened recently was, Jean-Paul Mercewal and Nat Duca, who are developers at Google, kind of published this document that's linked here that kind of covers some of the prototyping they're doing on some of the next-gen HardwareComposer and Gralloc interfaces. And they're planning to do this prototyping inside of the DRM HardwareComposer code. And so it's a really interesting document. Definitely think you should check it out. Going to try to kind of describe my sense of it at the moment. So when you look at kind of the classic HardwareComposer design, we've got this case where the way it's supposed to work is that Surface Flinger passes some number of layers, say 6 or something like that, to the HardwareComposer. The HardwareComposer then talks to the display driver and comes back and says, no, I can only do 4. And so then Surface Flinger will composite that down to just 4 layers and pass that through, and then the HardwareComposer will pass that to the display driver. And that's sort of how it's supposed to work. In practice, what tends to happen is the HardwareComposer that is written for a specific device, well, it's designed for a specific display controller that's on a specific SoC, which also has a specific GPU. And that GPU has, the properties that the vendors know about that they can say, okay, well, we can actually write a compositor that's faster than the default one. So we're just going to plug that inside of our HardwareComposer. So the HardwareComposer becomes kind of this very large blob of complicated code. And so when Surface Flinger says, here's 6 layers, can you draw that? It says, yep, thumbs up, I can do that. And you say, okay, well, here's 18 layers. Like, yep, I can do that. And so you can just, it doesn't really kind of follow the original protocol. And so when we looked at the DRM HardwareComposer, initially it had a very similar behavior. So basically it had this, when we see the green, I don't know if this is showing up very well in this, but the orange stuff is all device specific and the green's supposed to be all generic. And so you had this generic code that has a little bit of device specific code for the planner, and then also it had this precompositor that was fairly NVIDIA specific. But it followed sort of that same thing where it says, here's 6 layers, and the player's planner checks out with a DRM driver to see how many it really can do. But whatever, it tells Surface Flinger I can do it, and it'll squish it down to the number it needs. The problem with that, of course, is that that precompositor was NVIDIA specific. We couldn't use it. Nobody was using it, and so it basically got dropped. And so this is currently kind of how the DRM HardwareComposer looks at the moment. There's not a lot of device-specific code in it, obviously. It's fairly generic. And so if you look at the planning document that they pushed out, I'm going to push this over a little bit, there's sort of this thought of maybe Surface Flinger and the HardwareComposer can kind of become a larger blob. And basically just that device-specific stuff could be kind of popped out in some sort of pluggable way. And basically it would be able to do the negotiation and composite as it needs and then push that out to the DRM driver directly. And actually in the document they even talk about having different stages in the pipeline so that you might be able to have device-specific planner stage, device-specific GPU compositor, and being able to have Surface Flinger kind of manage those and the DRM drivers directly. And so this would be kind of an interesting approach, but it is fairly different than what we have currently. So it's interesting to see how this goes. Definitely check out the document, and it's open, I think, to comments, so you can add your own feedback. So suggestions out of all this. Stop using fbdev. Migrate to the DRMKMS drivers, please. Definitely please try to work with the community to get this, the DRM infrastructure expanded in order to support whatever needs you have. I definitely recommend sending your developers to XDC. Unfortunately, it's next week, so you're probably not going to make it this year, but next year, definitely send display developers to XDC. That's kind of the best place to really interact with the graphics community. And definitely upstream those DRM drivers. So here's credits, previous talks and slides that people have given that were very similar and kind of I used to generate these. Extra thanks to Jean-Paul, who's been very helpful in maintaining the DRM hardware composer and walking me through a lot of the changes. So I think that's it. And I've got 3 minutes for questions, so anything. All right, well, thank you so much.